what I want to tell you about today is what I think of as quantum detective stories. So I was intrigued by the beginning of the previous talk. I think in a very similar way, I think our job is to understand what's really going on in the universe, what a physical theory tells us about that universe, and what our observations tell us. And unlike the program that we were just hearing about, instead of beginning from the mathematical structure, I want to begin by thinking about what it is we can observe and asking whether there are things that we can observe that go beyond the current picture that we have of reality. So I'm going to tell you about two different experiments we've been working on and some other theory, investigating how much time atoms spend in a forbidden region and how much time photons spend inside atoms. But these are just two experimental examples to try to get our heads around what I think is this deeper, very important question about interpreting quantum mechanics. So before I begin, I'll show you a picture of where I am still stuck, although this picture is taken from an office I only had the chance to see for the first time in about a year, quite recently. And the names of the people who really did this work. So let me start by giving credit to this group of amazingly talented people and several generations of students who contributed to these experiments. The first experiment I'm going to be describing about these tunneling times using a Bose-Einstein condensate was built up over, as I say, many generations of students, beginning with Anna Joffrey, Mirko Zierka, and Chris Eleanor. But the most recent results are really due to Ramon Ramos, David Spearings, Isabelle Racicot, and most recently, Joseph McGowan and a few other contributors. And the experiments that I'll mention just at the end, which are still ongoing, were pioneered by Josiah Sinclair and have now been picked up by Daniela Angulo-Murcio and Kyle Thompson, along with a lot of theoretical support from Aaron Brodich and many, many others. So here's the big picture that I have in the back of my mind. Many of us want to know, is psi the whole story? And I'm not going to attempt to offer a final answer to that long-standing question. But I want to look at something we can probe experimentally. I want to ask, can I learn more about what a physical system was doing, what was happening, from subsequent observations? So here's a famous example related to the paradigm that we apply very often, the weak measurement paradigm, due to Aharonov, Albert, and Weidman. Imagine that I take some system and I put it in a superposition, A plus B. Is A plus B a complete description of what that system is doing at the current time? Or could I, for instance, learn by measuring that the system was in fact in B all the time? And usually the way, of course, we're trained to think about this is to say, no, that wave function really is the description of the system or of the ensemble until I find the particle in B. And then there's this mysterious collapse mechanism, or maybe there isn't. We don't need to argue about that right now. And at that point in time, things change. But of course, the situation gets more complicated if we observe something different. And one of the famous examples they looked at is equivalent to this. Suppose at a later point in time, I measure in a different basis, and I find the system to be in B plus C over root 2. What have I now learned about what it was doing? Must I just say it really was in A plus B until I collapsed it into B plus C? Or can I say I've gotten additional information about how likely the particle was to have been in A, B, and C individually? Have I learned something about the past, or have I just changed the system? And according to this interesting formalism, which is based entirely on physically observable effects, there's a good reason to say that the particle had to be in B, that we've learned that the particle was in B, quote unquote, all along. And this case maybe shouldn't be that surprising. If you think about what it would take to implement this experimentally, this is essentially an interferometer. I prepare a photon or a neutron in a superposition A plus B over root 2. I post-select using another beam splitter, B plus C over root 2. If I had drawn this picture this way, very few people would probably have taken any issue with the idea that by observing a photon at this detector, I learn that it followed the path B. That's the only path that connects my source to the detection, after all. There may be a separate question as to when the state changed. Right? Did it collapse when it hit this beam splitter? Did it collapse because it knew I was going to place a detector there? Or did it in fact only collapse when this detection event occurred? And I'm not going to try to address such philosophical questions. I don't even know if they're well posed. My argument is simply that once we see a particle at this detector, we really do learn that it followed B. And whether we've changed the state of events by making that detection or not is a separate question. I will say that towards the end of the talk, I want to mention some future experiments in theory that we've been doing that in a sense will actually investigate the dynamics of how a measurement like that modifies the system. And it's raised a lot of interesting questions I'm still very puzzled by. What I want to say for now is that was the trivia case. You can, of course, imagine much more general preparations, semi-coefficients times A, B, and C, and more general post-selections. For instance, A plus B plus C and A plus B minus C. And this is a famous, seemingly paradoxical situation that Weidman and Naharonov raised years ago. And the question is, how much can we learn about a quantum system in general when we make some final observation? Is there more to the best description of what was going on at these intermediate times than simply the wave function that we know about from the preparation? And to me, this comes back, of course, like everything, to the Bohr-Einstein debates or questions about delayed choice and quantum erasers. Can we do quantum archaeology? We have this conventional wisdom that when you see a photon reach some point on a screen, you're not allowed to draw certain conclusions about the past. You're not allowed, of course, to ask through which slit that particle went while it was traveling. But in the classical world, we know we do this all the time. We dig up some bone and we draw conclusions about what a dinosaur was doing 65 million or 100 million years ago. And the only point I want to make is most of us these days don't really believe that this dinosaur was classical. We believe that the world is described by quantum physics. And in that sense, when we're doing this or when we're thinking about cosmology or anything else, we are reasoning about the past of a quantum system. And therefore, instead of simply following Bohr or some caricature of Bohr and saying we're not allowed to make statements about the past, we should simply be asking which statements can we make? What is the degree of uncertainty about those statements? How much retrodiction can we do? So that's the overall background. As I said, I'm going to tell you about experiments we've been doing to try to illuminate these questions. I'll begin by introducing a long-standing puzzle over how long a particle takes to tunnel, and our recent experiment that in a certain sense probes the amount of time a particle spends physically in the forbidden region, classically forbidden region, before being transmitted. Explain why we're excited about doing some experiments that ask where was the atom while it was tunneling. Obviously, tunneling being such a paradigmatic quantum process, it's just interesting to ask these questions anyway. I've always wanted a picture of how the atom actually gets across. Where should I think of it as spending its time? But I think it also sheds light on this question of just how to think about the past in general. Do we learn more about what the particle was doing when we see, oh, this particle was transmitted, this particle was reflected? Finally, as I said, we'll talk about how that observation perturbs the tunneling, and in some sense, whether or not we can observe what it takes to collapse a system. And finally, I'll probably have to move superluminally to really get up to much of this, but I at least want to advertise our latest experiment on the archive, but not yet published in a peer-reviewed journal, about the converse question. When a photon traverses an atom cloud, asking how much time that photon spends trapped as a genie in a bottle, trapped as an excitation inside those atoms. And unlike the first question about tunneling, we don't even have a complete theory for this question. It's obviously solvable theoretically, but so far we don't have the solution, although we're working with Howard Wiseman on a procedure that we think ought to give the solution. But so far we have an experimental result for something that I don't think people knew how to calculate previously. So here's the motivation. Hopefully you're all familiar with the tunneling problem. I think for this audience, I don't need to spend a lot of time introducing it. I will, however, say that in a standard quantum textbook or quantum course, we learn how to calculate the probability of a particle making it to the far side, and we suppress any discussion of how long it takes before it shows up there. And of course, semi-classical solutions work pretty well above the barrier, but once E is less than V naught, the kinetic energy in some sense becomes negative. So if you even attempt a semi-classical solution, you get an imaginary time. And interestingly enough, imaginary numbers are going to crop up again in more accurate quantum treatments as well. Of course, the non-existence of a semi-classical time isn't the important thing. One can simulate the entire wave packet propagation or use some approximation such as stationary phase or steepest descent, find basically the group velocity or the group delay, if you prefer. When does the peak of this wave packet appear on the far side of the barrier? And that's been done for nearly 100 years. The thing is, all of these approaches are based on a phase accumulated as you traverse a region, hence stationary phase. And famously, a tunneling wave packet is decaying exponentially inside the barrier. It's a real exponential. It doesn't accumulate any phase. And one consequence is that in the limit of a thick barrier, the time delay becomes independent of that thickness. The phase is not changing as a function of d. And that means neither does the time. So if the time becomes independent of the thickness, then you can imagine that for a thick enough barrier, there comes a point where the time is less than d over c. The particle appears to appear faster than the speed of light. And this is not an artifact of the non-relativistic Schrodinger equation. And again, it's not the main topic of this talk. Many of you have heard about this before, some of you have not. I could go on and on. Suffice it to say, this has been observed by my group, or rather Ray Chow's group when I was a student there, and many other groups. The peak of the wave packet may in fact appear faster than a particle traveling at the vacuum velocity of light would be able to. And again, I won't go into this at length, but you can ask the obvious questions. Is energy traveling faster than the speed of light? The answer is no. Is information traveling faster than the speed of light? The answer is also no. Happy to discuss this with people who don't know the long story, but I won't take that time now. However, there's a more interesting question, which is to say, how long does an individual particle actually take to traverse the barrier? Not when does the peak of a wave packet occur, describing a fraction of the ensemble, but can we talk about the time a particle would actually spend interacting with something inside the barrier? This seemed like an important problem to many condensed matter physicists in the 1980s, notably Büttiker and Landauer, who spent a lot of time thinking about what's going on. And although I've had philosophers scold me for this, I'll take the simple-minded approach that to answer such questions, one has to ask first what it is one's going to do experimentally. One has to explain what one means by a clock. And in the end, the time is going to be what that clock measures. So we imagine these tunneling Heisenberg hedgehogs carrying little stopwatches that only tick while they're in the barrier. And we want to know when one hedgehog appears on the far side of the barrier, what will their clock show? I'll point out that in the past decade or so, there's been renewed excitement over measurements of tunneling times due to Ursula Keller's invention of the so-called Ado clock, and a number of other groups that have followed that up. It's a very different sort of time, even a very different sort of tunneling. I'm not going to be discussing it now, although I think they're really dramatic and exciting experiments. Instead, let's go back to some of the things that Büttiker and Landauer discussed, and one that goes back even further. I think this happens to be an especially elegant way of defining a clock, and it's due initially to Voss and Pivachenko, who suggested that if you want to clock the amount of time a particle spends in a region, you could consider a spin-polarized ensemble of particles moving towards that region and confine a magnetic field perpendicular to that initial spin in the region of interest. Then, of course, we know that while the spin is in the presence of a magnetic field, it will precess at the Larmor frequency. And you could imagine measuring the precession angle after the particle emerges on the far side, dividing by the lone Larmor frequency and extracting a time. That's essentially what we want to do with our atoms. We'd like to know when the particle is transmitted, what spin do we get? And the interesting thing here is the clock is carried by the particle itself. So we're not merely measuring a property of the overall wave function. We can't really look at the particle that is transmitted, or presumably at a different particle which is reflected, and measure what is its spin, and could conceivably get different answers for those two questions. That was something that even in the 1990s was controversial. There were people saying it's illegal to ask about the time spent in the barrier and to simultaneously ask whether a particle is transmitted or reflected, because those two questions correspond to non-commuting observables. And I would argue, based on experiments like this, that that's really not a problem. One can look at a sub-ensemble defined by transmission and still ask, what does the clock show in that case? So how do we do this experimentally? First of all, what's the system that we want to use? We're going to use cold atoms. We begin with a Bose-Einstein condensate of rubidium-87. The Bose-Einstein condensate nature isn't very important. This is essentially an atom laser. We want something with a long coherence length so that we can see a significant tunneling probability. We cool it to the point where its coherence length, its thermal de Broglie wavelength, if you prefer, is on the order of 4 microns. And since we can form barriers for atoms by focusing light beams down, detuned to the blue of the atomic resonance, we can actually use essentially a microscope to focus this blue light to about 1 micron, which is now smaller than the wavelength of the atoms, the necessary condition for getting significant tunneling probability. The barrier height is about 150 nanokelvins, which is much higher than the 1 nanokelvin temperature of the atoms. And just to give a sense of scale, this corresponds to a critical incident velocity of about 4 millimeters a second. So a very different scale from what you would imagine in electron tunneling or in the strong field ionization of that Otto clock experiment. Basically, if we could push these atoms at 5 millimeters a second, essentially all of them would travel through that focused laser beam. If we push them at 3 millimeters a second, they're essentially all repelled and reflected by that same laser beam. So we begin with a BEC around 100 nanokelvin. We use delta kick cooling, a kind of matter wave lensing, to cool down as low as 900 picokelvin. And there's a time of flight measurement that shows that over the course of about 60 milliseconds, this 20 micron cloud has hardly expanded at all. And we're going to fire them very slowly at this barrier made of the focused blue detuned laser beam. Here's a video not in the current configuration, but of atoms sitting on top of a blue sheet of light and trying to tunnel through. Most of them, as you see, just spill over the edges instead. Now, of course, we also need this clock. We need the probe, that Larmor rotation. We don't know how to localize a magnetic field to that 1 micron region. However, we can generate a fictitious magnetic field by coupling any pair of states, right? Every two-level system acts like a spin 1/2. In our case, we use what are known as the clock states, the m equals 0 sublevels of the f equals 1 and f equals 2 hyperfine states, the ground state manifold of rubidium-87. These are the states that would be used, for instance, in an atomic clock, right? These are the states that in cesium are still used as the definition of the second because they're relatively insensitive to outside perturbations. And we couple these not with microwaves, but with Raman beams, with a pair of laser beams detuned by this 6.8 gigahertz splitting so that a 2-photon transition can couple them. And the idea is that we could, in principle, focus those Raman beams somewhere within the barrier. In practice, what we do right now is we use the barrier beam itself as a Raman coupling as well. We modulate the barrier, frequency modulated, at 6.8 gigahertz, generating a sideband so that the carrier and the sideband have to filter out the other one, act as this pair of beams, coherently coupling the f equals 1 and f equals 2 states. And that's going to act as our Larmor rotation. So here's the overall experimental sequence. We condense the atoms in a crossed dipole trap, attractive potentials due to 2 laser beams. But then we turn off one of those beams. So the atoms are now trapped in a single red laser beam moving horizontally that acts as a kind of waveguide for the atoms to allow us to perform one-dimensional experiments. We then superpose on the focus of that waveguide our blue detuned barrier. And with a magnetic field gradient, we can push the atoms towards that barrier that also, due to the modulation, is acting as a pseudomagnetic field, and look at either the transmitted or the reflected cloud. We then do a Stern-Gerlach measurement. In initial versions of the experiment, we actually physically separated 2 spin components using a field gradient. We've moved on to a less noisy way of doing these measurements. But here was an early picture. Our atoms were all transmitted because we had turned off the barrier, and we could measure the plus x and minus x components, which allowed us to extract the angle. Here's the angle as a function of velocity. We confirmed that under free evolution, the time spent in a region went as 1 over the velocity. So very exciting. More importantly, it allowed us to calibrate the strength of that interaction, calibrate the rotation rate of our clock. And of course, if we then turn on the barrier, we see a reflected cloud shown here on the left and a transmitted cloud. And we get different splittings on the 2 sides between the plus x and minus x components. For full disclosure, the reflected cloud is a much more complicated situation due to atom-atom interactions. We're currently writing a paper about that. So I'm going to focus on the transmitted cloud. And here were some of our earliest good data. As a function of incident velocity, over here, the critical velocity to surmount the barrier was about 5.1 millimeters per second. And we see this initial 1 over v, sort of semi-classical dependence. But at some point, interestingly enough, the time begins to drop again. And you shouldn't entirely trust these data. You should take them with a pillar of salt. But this is fascinating because there were theoretical predictions that at low enough energies, the time should actually begin to drop instead of continuing to climb. However, there was a complication. The complication goes back to the work by Büttiker in 1983, where he sort of popularized this Larmor clock. And he thought rather deeply about how the Larmor clock works. And I think it should be obvious to most of you that the reason for this precession is because you can think of this initial spin polarized along the x direction as a superposition of spin up and spin down, an equal superposition. And although those are both eigenstates of the Hamiltonian, they have different energies due to this B naught when they're in the barrier region. And that, in fact, means that they're going to pick up different phase shifts, and that relative phase is the precession angle in the equatorial plane here. What Büttiker recognized, however, is that they also have different tunneling probabilities. The one that's aligned with B naught sees a potential energy suppressed by the Zeeman interaction, while the other one sees an elevated interaction energy, and the transmission probability is exponentially sensitive to that energy deficit. Therefore, the aligned spin is more likely to be transmitted than the anti-aligned spin. And in addition to precession, we're going to see some tendency to align. Now, I think Bass and Rybachenko had been aware of this, and essentially their idea was just to take the limit as B naught goes to 0 and look at the residual interaction. Figure that was an essentially non-disturbing measurement. What Büttiker pointed out is that both of these effects, the in-plane precession and the out-of-plane alignment angle, are linear in the field B naught. So even as you take that limit, you can't neglect the tendency of the spin to align with the magnetic field. Again, not align due to any torque. There's no torque in that direction, just align due to a precession. If you look at the overall wave function, there will be no change in SZ, it's conserved. It's just that the plus Z are more likely to be transmitted and the minus Z more likely to be reflected, all right? So Büttiker reasoned that there are actually at least two quantities that look like angles, and therefore two quantities with the dimension of time once you divide by the Larmor frequency. And I think it was complicated to understand why there should be two different times. So he just added them in quadrature and said, well, maybe the three-dimensional angle is really the important one. The fascinating thing to me is that a Feynman path approach led to complex times. This is something pioneered by Sokolovsky and Baskin. And the real and the imaginary parts of those complex times, even though it was completely unclear what their physical relevance would be, are equal to the in-plane and out-of-plane angles here. And later on, I showed that you could unify these approaches by thinking in terms of that weak measurement formalism of Aharonov and his collaborators, to which I alluded earlier in this talk. In this formalism, one often finds complex values for things that one measures on post-selected ensembles, but there's a very definite down-to-earth physical distinction between the real and the imaginary parts. The real part describes the shift that you get in a pointer position if you couple to some measuring apparatus, while the imaginary part reflects something about the back action of the measurement, the fact that doing the measurement actually disturbed the post-selection probability. As we saw here, right? Placing that magnetic field in the barrier changed the likelihood for a spin-up or a spin-down particle to even make it to the post-selection regime. All right. So taking this into account, we realized that we need to measure not just the equatorial angle, but the full spin in 3 dimensions. And that's what we did. It meant we had to develop techniques for doing full tomography on the pseudo-spin of these transmitted atoms, which my students managed to do remarkably well. This is truly a heroic experiment. I can't stress that enough, how impressed I am with the people who made this thing finally work. And again, we begin with spins polarized along the x direction, which for us is just one of those hyperfine ground states. And what we see as we lower the velocity, so you spend at first more and more time in the tunneling region, is that you first begin to precess in the equatorial plane and then align with the plus. And here are 2 projections showing that. That means we were finally able to extract not just one number, but these 2 numbers, the real and imaginary times from the weak value perspective, or the in-plane and out-of-plane angles from a more physical viewpoint. And what we see, there's a little complication on this slide, in part because we don't have monochromatic pulses entering the barrier. But the big story is that as we go to lower energies, you first see the real part, the actual measurement outcome, so to speak, grow. And then it seems like it does begin to drop again. And this shaded region shows the theoretical predictions. That disagrees, of course, with the semi-classical or so-called Büttiker-Landauer time that would diverge at the barrier height, although honestly, no one, including Büttiker and Landauer, expected that divergence to be physically significant exactly at that resonance. And one sees the necessity of this out-of-plane time, imaginary part, that talks about back action, essentially only once you get into the quantum regime, once your incident energy is roughly lower than the height of the barrier where back action becomes important. More recently, we've been able to clean these data up, get deeper into the barrier regime, into the tunneling regime, begin with lower velocity spreads, and even measure for two different barrier heights. So now we've really confirmed that if you look, for instance, at these red points, as you go to lower energies, the time clearly does begin to drop. And in fact, the red data are for a higher barrier than the blue data, and you clearly see that for the higher barrier, the time is smaller. So this is something I call the red light effect, that you're less likely to get across the street when the light turns red, but if you do get across, you probably got across more quickly. So we're continuing to investigate this. That latest work is going to show up in PRL soon. And as I said, we have some more complicated work addressing what happens in reflection. It remains really, really interesting. The thing that I really want to get to with these experiments, though, is a local Larmor clock, not just asking how long did the particle spend in the barrier region, but how much can we say about what the particle is doing on its way to the far side. We could imagine localizing these Raman beams, this probe, only to the entrance of the barrier or to some other region within the barrier. And what we really want to do then is measure whether the transmitted and reflected particles have a different history, whether some of them spend time in one region and others spend time in another region. That remains experimentally challenging, but we do have theory predicting what we should see once we find out how to do it. And the fascinating thing is that although for a symmetric barrier, we actually expect the same amount of time to be spent in the barrier region, regardless of whether a particle is transmitted or reflected. Once you zoom in and ask where was the particle, you see something very different. And it's somewhat intuitive. If we looked only at reflected particles, we'd expect them essentially only to spend time in the first evanescent decay region of the barrier, here schematically shown extending from -1 to 1 micron. And that makes sense, right? Psi squared is only significant in that first exponential decay region. On the other hand, if you post-select on transmitted particles, well, then you do learn something by detecting the particle on the right-hand side of the barrier. The time reversibility of the Schrodinger equation should give you a sense that you've learned just as much about the time the particle spent near the exit as you have about the time spent near the entrance. And indeed, the prediction is completely symmetric. You spend time within an evanescent decay length of the entrance and of the exit. Confusingly, you spend essentially no time, exponentially little time near the center of the barrier. And yet the integral under these curves is equal. And that's why we want to zoom in and really spatially localize them. One caveat I'll mention in passing, these are calculations for that real part. And I should admit that the imaginary part doesn't behave like this at all. The imaginary part is roughly constant across the barrier. So if you're unhappy with the claim that particles make it from one side of the barrier to the other without spending any time in the middle, then you can point out correctly that they do spend time in the middle, but from this, using this language anyway, the amount of time they spend in the middle is imaginary. What that really means is that as a particle traverses the barrier, it will have vanishing little effect on a probe which was interacting only with particles at x equals 0. On the flip side, a probe interacting with x equals 0 can effectively suppress the tunneling. And in fact, by a WKB approximation, you'll see that the particle's likelihood of being transmitted is roughly equally sensitive to a disturbance anywhere along the thickness of the barrier. All right, I realize I can't see any people, but I think I have about 10 more minutes of talking. Hope someone will leap in and correct me if I overstay my welcome. I apologize in advance for having no feedback on this. We began thinking about how exactly the act of looking for the particle modifies its behavior. And this is something I began thinking about thanks to an interjection by Bill Phillips at a conference now over 20 years ago, which I answered incorrectly in the paper cited down here, which is why bother with these weak measurements, this B goes to 0 limit? What would happen if I just looked strongly for a particle in the barrier region? And at the time, I answered very glibly that if you looked strongly enough that you could tell with certainty, hey, that particle is in the barrier. I see, an image over here on a screen. Then all bets would be off, because by so doing, you would collapse the particle to be in the barrier region. And of course, any wave packet localized within the barrier has enough energy to be in the barrier. You're no longer looking at tunneling. And in fact, I said at this point, the particle would be basically equally likely to roll over to the right or to the left. And I've been thinking ever since then, it would be wonderful to do an experiment where we could show that the mere act of looking for particles inside the barrier with spatial resolution better than the width of that evanescent decay could enhance the tunnel. Even for an arbitrarily thick barrier where I saw zero transmission, I'd start seeing particles get across because the act of measuring had to give them that extra energy. Well, we began thinking about how to do that. You could imagine, for instance, not having a weak magnetic field, but a strong magnetic field that acted as a pi pulse that rotated the spin by 180 degrees. And then, of course, if I see a particle at minus x instead of plus x, I know that it was definitely in that region. Of course, to make a pi pulse, you need to know the duration of the pulse. And the whole problem here was we don't really know how to talk about how much time a particle spends in a given region in the first place. But a few years ago, it occurred to us that maybe we could do something else. Stick with the weak magnetic field, pseudomagnetic field, that we've been using that gives you only a small rotation in the equatorial plane. But then ask what happens if I post-select a particle in the minus x state. This is sort of like unambiguous state discrimination, right? I have a particle that if it wasn't in this region is still along x, and if it was in this region is now at some small angle theta. But if I post-select on minus x, orthogonal to the initial state, that post-selection can only succeed if the particle saw the magnetic field. So the question is, does this count as a kind of collapse? When I find a particle in the minus x state, have I now learned that the particle was in the presence of that magnetic field probe? And can I therefore probe the effect of collapse? So we decided to calculate, and one day hopefully measure, what the ratio of the transmission and reflection probabilities should be, given that I had an interaction at some position x, I could imagine moving that probe around again, and that I looked only at the particles that were finally in the state minus x. Does that post-selection guarantee that the particle has enough energy to make transmission and reflection equally likely, particularly? And the answer is no. If the probe is on all the time, then I have a time-independent interaction, energy is conserved, and there's no way that I could give the particle extra energy. And in some sense, this was confirmed by the first calculations that my student David Spearings did on this. Over here, we're mapping that ratio, transmission probability to reflected probability on a log scale, as a function of the position of the probe within that hypothetical 2-micron barrier. And these straight lines mean that we always see an exponential dependence. In other words, the particle is always exponentially more likely to get out the side that the probe was on. The interesting thing is, of course, the slope here turns out just to be that e to the minus 2 kappa x. And this looks as though when I do this measurement, I have indeed learned where the particle is, but I haven't given it any energy. So it still has to tunnel out either to the left or to the right. And that's why the ratio depends on the difference between x and d minus x. And if the probe is at the middle, I do indeed find equal probabilities to be on either side. In any case, that wasn't what we were looking for, although we found it very interesting. It's easy, in fact, to show analytically why it has to have this form. We should have known it before we started. But this made us realize what we need to do is have that probe itself be time dependent, to pulse this effective magnetic field on and off, and then post-select on atoms that are in the minus x state and ask what that ratio is. So as a function of the duration of this probe pulse, David repeated those calculations. And again, for the time-independent probe, you just see this straight line. As you make the probe faster and faster, you approach this green curve, where indeed, regardless of where the probe is in the barrier, you have essentially equal probability to be transmitted or reflected. And you can dig down into the simulations and confirm that when you have these probes, if you post-select on the minus x state, you find the particle really has been given enough energy to traverse the barrier. And in the delta function, when that again, this becomes analytically solvable, and we can show that this is in fact mathematically equivalent to preparing a wave function in the probe region, where, of course, it has enough energy to be there, and for high enough energies, it's equally likely to be transmitted or reflected. For us, however, what's interesting is asking, where does this transition occur? How short must the time be for which I pulse this probe on and off in order to see this behave like a collapse? And these simulations are hard and fast. This is just doing math, and the experiment will be just doing the experiment. The hand waving that comes behind it that I think is really interesting is the following. If I had a delta function probe, then when I see a particle along minus x, I know that the particle was in the probe region at the instant of time at which I turned the probe on. On the other hand, if the probe is on for 1 millisecond, then when I find a particle at some position, with a spin minus x, I know that it must have been in the region at some point during that millisecond. The question is, does that teach me that the particle was ever definitely in the barrier? Because remember, if I have a time-independent probe, then by seeing the spin rotate, I learn that the particle was in the barrier at some point in time, but that's not sufficient to collapse it, right? In some sense, the entire time-independent wave function was in the barrier at some point in time. I would argue that unless we know that there is a point in time at which the particle was definitely entirely within the wave packet, within the barrier, we haven't collapsed it. So in some sense, we're learning something about how long it takes a particle to leak out of the barrier. Is that millisecond enough that by the time the probe pulse is over, the particle might not be within the barrier anymore? Anyway, we're still developing our way of thinking about this, but I think it raises really interesting questions about quantum measurement. And I think it's something that's going to be accessible in our laboratory. So if I still have 5 minutes, which I think I do, I will give you this preview of the experiment. It's up on the archive over here, and that I think is beginning a new chapter. The previous experiment asked how much time an atom spends inside a light beam. And by coincidence, on a different experiment of ours, we started asking how much time a photon spends inside an atom, as in this picture over here. This began with a series of experiments where we were looking at quantum information, how to make quantum logic gates or do quantum non-demolition by using optical nonlinearity. And I'll just remind those of you who don't think a lot about nonlinear optics what we mean by that. What we mean is that two different light beams can have an effect on one another, so we can use one to measure what the other one was doing. And in particular, when you send light through a cloud of atoms, these photons, often called pump photons, can be absorbed, exciting atoms, and that bleaches the sample. It makes it look more transparent. And that would reduce the phase shift seen by a probe. It changes the index of refraction. So the question that we started asking is, as I send photons into this cloud, some of them are absorbed and some of them are transmitted. But if the photon is transmitted, does that mean that it never excited any atom? The naive picture would say, once I excite an atom in a case like this with a single photon, it has no particular reason to decay in any particular direction. It's going to spontaneously emit into 4 pi, and mostly those photons will not be transmitted. So when I look at a transmitted photon, am I just selecting the photons that never turned into atomic excitations? If they never turned into atomic excitations, a separate probe would be unaware of them. And that's the experimental question that we started asking. Some people we discussed this with, including a former student of mine, argued, no, that's the wrong way to think about it. All the light that's going through the cloud polarizes the medium, and that polarization includes some amplitude to be in the excited state. And by this logic, the transmitted atom has polarized the entire medium because it went all the way through, while the absorbed photons were on average absorbed in the first absorption length of the cloud. So maybe we should see a greater phase shift for transmitted atoms than for reflected atoms. Photons. So here's what the experiment looks like. Again, as a cartoon, we send these so-called pump photons through the sample while sending a probe beam through in a different direction. We measure the probe, and that phase shift we see as a stand-in for the amount of time atoms spent in the excited state. That's what the probe is sensitive to. However, we can also place a detector at the far side to ask whether a pump photon is transmitted or reflected. And if we condition this measurement on detection of a photon, we learn how much time atoms spent in the excited state due either to transmitted or absorbed photons. And again, you can go to the archive to read the details. I won't have time to explain the whole experiment. It's done with a cold atom system. It's based on two previous experiments where basically we learned that the difference between a phase shift when you get a click and a phase shift when you don't get a click can teach you what one extra photon was doing, even if your source is, as in these experiments, a coherent state source. And here's just some description of how the data acquisition and analysis went. Again, I'm happy to discuss this at more length with any people who want the technical details. This took several months, about 600 hours of sleepless data. And in the end, although it looks rather messy, it's clearly statistically significant. We learned that in our case, with 20 nanosecond pulses, even transmitted photons that didn't seem to be absorbed by the atoms did cause atoms to spend time in the excited state. And as I said, we have some models for how you might think about this. The models are basically semi-classical at the moment. And our data point sits inconveniently between two of these models, although we have other reasons to doubt one of them. And we're working with Howard Wiseman and others right now to try to do a correct quantum treatment and answer what seems like a pretty straightforward question. As a photon is transmitted through an atom cloud, how much time does it spend trapped inside the atoms? I think, years ago when I heard about this picture of how photons get through atom clouds, I thought of it as simply a nice picture to have in my mind, but something not experimentally verifiable. And what we're seeing once more here is there are real experimental ways to ask these sorts of questions, to look at sub-ensembles while probing something about what the system was doing before it got to that final state, which I think offers new insight into how we should think about the system evolving. What should I think of the photon having actually done while it made it through that sample? So I hope that you all find these questions interesting as well, and maybe come up with other questions that we can address experimentally along the same lines, or different ways that we should be thinking about the ones we're discussing right now. But to sum up, we did measure both components of this Larmor weak value to tunneling time. They're on the order of a millisecond, as they kind of have to be given the scales of our problem, but they also agree with these interesting predictions, dropping time at low energies. We also expect to be able to collapse atoms into the barrier region, and I think there are deep questions about the timescales required to do that. And we don't know any way of analytically predicting that timescale. So far, we're still just doing these numerical simulations and some limits analytically. And finally, we're now starting a series of experiments. We have that one data point, but obviously we need more to look at how long resonant photons, which are transmitted, cause atoms to spend in the excited state. We have some semi-classical pictures to explain why maybe we should have expected the results to turn out the way they did. But the real description of the problem requires treating the entanglement of all of these different optical beams. And so far, that remains a really complicated question. All right, so with that, I'll thank you again for your attention and invite questions.
Okay, thank you. Yeah, thanks for the nice talk. I'm not sure is there any question? No online questions? Well, Valeria.
Hi. I wanted to ask a question about the, so you see in most of experiments we have post-selected or at least looked at the transmitted wave packet, and okay, you get some results. If you were to post-select on the reflected wave packet, maybe you've done it, I've not seen it, but would you see any difference in this time that the particle spends in the barrier?
Right. So as I said, theoretically, for a symmetric barrier, it turns out you get the same time if you measure the entire barrier. Now, our barrier isn't perfectly symmetric. We do the best we can, but we do, in fact, look at the reflected cloud as well. And we didn't find the same number, which confused us at first. Now, what we've now learned is that because as a wave packet approaches the barrier, it generates this very strong standing wave. The interactions between atoms have a huge effect on the reflected cloud. And we're beginning to model that and understand what really happens to the spin of the reflected cloud. But the idea that the spin is a kind of unperturbed clock seems to work well for the transmitted atoms and not for reflected atoms, at least unless we go to a Feshbach resonance where we can turn off the interactions. To be honest, with that experiment, we're probing something that I knew how to calculate 25 years ago. I think it's important to do because most physicists aren't aware of the answer, but we are really confirming calculations, unlike this final experiment. One thing that most atomic physicists find more interesting is what happens once you do include those interactions, because there, we don't even really have a prediction. And the question of how long one atom in a strongly interacting cloud spends in the barrier region is obviously a much more complicated one than the question of just an isolated single particle. And it kind of raises questions of what happens when you measure a system and allow it to interact with an environment, or maybe you begin to traverse a kind of quantum classical boundary. But the short answer is yes, we have measured that. We're beginning to understand it. I don't present it because it turns out the story is more complicated.
Are there more questions? No? Well, thanks again for the talk.
Thank you very much.